Welcome to the final recording on quadratics. This section we're going to have a look at how we can use quadratic equations to model real-life scenarios. So the previous two lessons have been through this as well, but it really is a crucial skill to master, not just for the pure aspect of the course, but also the mechanics side too, where you may see questions involving modelling mechanics. And so this bit of quadratics can be seen in both mechanics papers and pure papers too. So before we get going with some more examples I've thought up myself to do for you to try, I want you to work through these 4 examples if possible. So try them first, as ever, and then once you've had a go at them, if you could press play on the video and see if your solutions match my own. So let's have a look together at the solution to question 1. So in question 1, we're told to try this without a calculator to simplify this expression, giving the answer in the form p root 3 minus q, where p and q are both positive rational numbers. So I'm just going to write this expression out first, the 6 root 3 minus 4, all over 8 minus root 3. We need to remember this idea of rationalising the denominator. So what we can do to make the bottom rational is multiply the top and the bottom by the conjugate of this. Now the conjugate is just this thing exactly, but the minus switched to a plus. That's all we change. So this is a conjugate of that. So when we do this, what we're going to have on the bottom is just simply the difference of 2 squares. So on the bottom, what we're going to have is 8 squared minus root 3 squared, which will be 64. And root 3 squared is 3. On the top, this will be expanding out to binomials. So 6 root 3 multiplied by 8, that gives us 48 root 3. 6 root 3 times root 3 again. Root 3 times root 3 becomes 3, so 6 times 3 is 18. Then minus 4 times 8, that's minus 32. And finally minus 4 multiplied by root 3, which is minus 4 root 3. So if we simplify these bits here, 48 root 3 minus 4 root 3, overall that's 44 root 3. And 18 minus 32, that can be simplified together, and that's going to become minus 14. And all of that is going to be over 64 minus 3, so that's going to be over 61. But rewriting it in this particular form, where it's p root 3 minus q, we can just section out this denominator twice. So we can say it's 44 over 61, lots of root 3, minus 14 over 61. And so in our case, I'm just saying that p is 44 over 61 and q is 14. So 14 over 61 rather. Question 2, find using algebra all real solutions to this equation here. So we have 16a squared equals 2 root a. What we can do first of all is divide both sides of this equation by 2. We then get 8a squared equals root a. At this stage, we can now square both sides of the equation. So if we square both sides, that just helps us to neaten it up and simplify. So first of all, if we square both sides, the 8a squared, 8 squared is going to become 64, and a squared all squared is a to the power 4. The square root of a multiplied by itself just gives us a. We can now factorise by bringing it first of all to the same side of the equation and setting it equal to 0. Like I say, we can now factorise because we have a common factor here of a. So we can say that's a brackets 64 a cubed minus 1 equals 0. So we can now see quite clearly that one solution is that a could be equal to 0. So we can say a equals 0, or might be another solution if this is equal to 0. So it might be the case instead that 64a cubed minus 1 is equal to 0. If that's the case, we'd have 64a cubed is equal to 1. We can then divide through by 64 to obtain that a cubed must be 1 over 64. Then to go from a cubed to a, we could cube root 1 over 64. The cube root of 1 is 1, the cube root of 64 is 4. So the other option is that a is a quarter. So we've got the two options for a, the two possible solutions for it in red, either 0 or a quarter. Question 3, what we have here, if you remember, well done if you do, this one's a hidden quadratic. So this thing here looks an absolute mess, it looks quite ugly, 8 to the power x minus 1. But whatever that is, it's that thing there squared minus 18 lots of the same something plus 32 equals 0. So we can make a substitution. What we can do is say let big X, or some other letter if you like, equal 8 to the power x minus 1. Then what we'd have is this just becomes big X squared minus 18x plus 32 equals 0. Okay, so all we've done here is just swapped the 8 to the power x minus 1 with this big X. You can now see this quite easily factorizes. So we need two numbers that multiply together to give us 32. Yeah, when we add them, it gives us negative 18. Those two numbers would be, in some order, minus 2 and minus 16. So therefore, big X has to be 2, or we must have that big X is equal to 16, one or the other. But obviously this equation wasn't in terms of big X, we've just invented this to make it easier. We now need to remember what big X was. It was 8 to the power x minus 1. So we can now say that 8 to the power x minus 1 equals 2, or 8 to the power x minus 1 equals 16. Now initially that doesn't look like it helps us at all. 8 to some power gives us 2, that's not that obvious to see. Same with 8 to some power gives us 16. We could find that power, but what I'd suggest is to think that 2 and 16 are both powers of 2. So could we rewrite 8 as a power of 2? And of course we can, because 8 is 2 cubed. So what we're going to do in this next step is just replace 8 with 2 cubed. So either 2 cubed to the power x minus 1 is 2, or 2 cubed to the power x minus 1 is 16. So all I've done on this step is just said, well, we can replace this 8 here with 2 cubed. That's all we've done. Now using the power of a power idea, we can multiply these two powers together. So 3 times x minus 1, that gives us 2 to the power 3x minus 3 equals 2. Or we could have this 2 to the power of 3x minus 3 equals 16. But before I write 16, let's see if we can rewrite this with the same base. Could we rewrite 16 as a power of 2? And of course we could. 16 is 2 to the power 4. In the same way here, 2 on its own is just the same as 2 to the power 1. So what we've got now is two new equations relating x and these constants. So either we can have that 3x minus 3 has to be 1 to make these equal, or it could be that 3x minus 3 is actually equal to 4. So now we can solve these two linear equations. So it could be, like I've said, that 3x minus 3 equals 1. And if that's the case, this is fairly easy to solve. Just add 3 to both sides and then divide 3 by 3. So therefore, one solution is that x equals 4 divided by 3, in other words 4/3. Or, of course, we have this purple option here. It could be that we have 3x minus 3 is equal to 4. So if it's this option, we can solve it in the same way. Add 3 to both sides, 3x equals 7, and then divide through by 3. We then get that x equals 7 over 3. And so we have these two possible solutions for x. Either x is 4/3 or x is 7/3. Finally, for the warm-up, we have another hidden quadratic. We need to solve b to the power 4 plus 7b squared minus 18 equals 0. Again, in the same way, what we could do is introduce this idea of big X and set this equal to b squared. We do that because b to the power 4 is the same as b squared squared. So if we introduce x as b squared, what this would give us is x squared, because this is b squared squared, which is b to the power 4, plus 7 lots of b squared, that becomes 7 lots of x, minus 18 stays as it is, equals 0. So again, we can solve this in the normal quadratic way, find two numbers that multiply together to give negative 18 and add to 7. Well, those two numbers are positive 9 and minus 2. So therefore, either big X equals negative 9 or big X equals positive 2. Big X was b squared, so reintroduce b squared. So either b squared is negative 9 or b squared equals 2. If b squared was equal to negative 9, b would be the square root of negative 9, which has no real number solutions. And so we have no real solutions to this. Or, in terms of real solutions, this does have a real solution because we can square root a positive number. So from this one here, we can find two solutions. So if we square root and consider both positive and negative options, we get that either b is negative root 2 or that b is positive root 2. Remember, if you've got something squared equals a number, consider both positive and negative square root options, otherwise you're in real danger of losing 1 mark, which sounds trivial, but that 1 mark can make the difference between a grade. And so that's all the warm-up questions completed. Alright, so we've done the warm-up questions. This lesson now, as I've said, is just a way of getting even more practice on modelling quadratics. So there's no exercise in the book after this as such. It's just 4 questions I've made and adapted myself from other questions, just to give you some much needed practice to get mastery with this very important topic. So the idea is to do these questions on your own, see how you get on, and then on your worksheet I've got the answers on the back of it, which just give you a brief idea of how to come to the solutions. This video will, however, talk you through step by every step how to arrive at the solutions written on the end sheet of the notes. So let's have a careful talk through of the first question. So question 1, we have a striker practicing a free kick in a game of football, shooting towards the goal. There's no goalkeeper, so this person is just practicing their trajectory and speed, presumably. The ball's kicked from the ground directly towards the goal and reaches a maximum height of 2.89 metres at a horizontal distance of 17 metres from the free kick spot. So we can add this little thing, bit of information on our diagram. So we're looking at this point here. So 2.89 metres high at a horizontal distance of 17 metres from the free kick spot. The ball can be modelled as moving in a vertical plane following a parabolic path, as in this graph. So for question part A, we need to use these initial conditions and a coordinate diagram to find a quadratic equation for the trajectory of the ball in this form. So what we need to do here, if this is the form we need, this is called the root form of the equation. And so by symmetry, we can work out what the roots are. And so one root is where x equals 0. Whoops, that's a mistake of mine. So one root is x equals 0, as in here, is at a maximum height at 17. And by symmetry, it would come down again and hit the ground at 34. Remember, the maximum or minimum is always halfway in between the roots. And so if a maximum is 17 and one root's 0, 17 the other side of the maximum will be 34. So the other root is x being equal to 34. And so we can substitute this into our equation here. We'd then have that y equals a brackets x minus 0 brackets x minus 34. But x minus 0 is just x, and so then we'd have ax brackets x minus 34. We're again told, though, that the maximum height is 2.89, 17 meters away. And so we can substitute this into our equation. So now we can sub in the coordinates 17 and 2.89. So y is 2.89 when x is 17. So 2.89 will equal a times x, which is 17, multiplied by x minus 34, which is minus 17. In other words, 2.89 equals 17 times minus 17 times a. So let's use a calculator for this one. So 17 squared, essentially, and the minus of that is 289. So 2.89 equals minus 289a. So therefore, a will be 2.89 divided by minus 289, which is minus 0.01. So the equation of this parabola is going to therefore be that y equals minus 0.01 x brackets x minus 34. Part B of this question, we're told that the centre of the goal is 20 metres away from where the ball was kicked, and the height of the goal is 2.44 metres. The crossbar, which is the top of the goal for the non-footballing fans, myself included actually, that can be modelled as a horizontal line of height 2.44 metres. Use your model from Part A to determine if the ball will enter the goal. So at this point we need to remember what we just put down for the model from Part A. The model from Part A is this thing here. And so all we need to do now is think about what the height will be when x is 20. And so we can substitute in when x is 20 to see what the height of this ball will be. If the height is 2.44 or less, the ball will go into the goal. If height's over 2.44, the ball's going to sail over the crossbar and miss the goal. So let's see what y is when x is 20. We then have minus 0.01. Whoops, not 0.00. What I'm thinking there. Times 20. Brackets 20 minus 34. So let's use the calculator to find what value this gives us for y. So minus 0.01 times 20. Brackets 20 minus 34. That gives us 2.8 meters. And 2.8 is bigger than 2.44. Therefore, ball will not enter the goal. It's too high. So unfortunately, that shot is far too high. For part C, we need to give one possible limitation of the model, or criticism. So any valid criticism will do. And so it could be one of a few things. So one possible criticism is we're assuming no air resistance. So this model assumes no air resistance, whereas in real life there will be some air resistance, and that will have some effect. Or you could say that this model assumes that the ground is perfectly horizontal. No ground is perfectly horizontal, so the football goal will either be slightly different to 2.44 meters high in some direction. So it assumes the ground is perfectly horizontal. It almost definitely isn't. And to be honest, as long as your criticism makes sense and is a valid criticism, you can put more or less anything as long as it's true. So you could be saying as well, for example, that it assumes there's no spin on the ball. Or swerve, like if the ball curves, that will affect its flight time and flight path. So it assumes no spin or swerve on the ball, which almost definitely is not true. You could say the ball is assumed to be a point particle. Obviously it's not, it's more than a point, it's roughly a sphere. We're also assuming here that the crossbar is infinitely thin. So we're assuming that the crossbar has no thickness, which again isn't true. Using this model, the ball would either be going under the crossbar and in, or over and missing. So obviously in real life, it's possible that it could actually hit the crossbar itself and bounce off. So this model is too simple to account for that possibility. But anyway, that's question 1 sorted out. Question 2 of these questions. So here we've got a suspension bridge which has twin towers that extend 75 meters above a road surface and are 400 meters apart. And each tower is at either end of a bridge. The suspension cables are parabolic in shape and they touch the road at the center of the bridge. So that's the diagram. This is an actual bridge, and here it is transformed onto a set of axes for us to model. X and Y on these axes are given in meters. So for part A, we need to find an equation that models the path of the suspension cables and links the height of the cables above the road, Y, to the distance along the bridge, X. So we use the provided coordinate system, i.e. use this. Give the equation in the form y equals a, brackets x minus h all squared, plus k, where a, h and k are constants to be found. So if we need to rewrite this equation in this particular form, we need to remember that if we rewrite the quadratic in completed square form, then h and k relate to the turning point of the quadratic, where h is the x-coordinate of the turning point, and k is the y-coordinate at the turning point. So the turning point is actually here. Okay, so this parabola has got a minimum at this point here, which we can see. So all we need to work out is what is the coordinate of that point. Well, here's where we can read the question. So we're told that these cables touch the road at the center of the bridge. And so if a bridge is 400 meters along from one end of the twin tower to the other, then halfway between them, in the middle, the center, that's going to be at 200 meters. So the height of the cables at 200 meters is 0. They're 0 meters above the road. In other words, they touch the road at the center of the bridge, which is what the question says. Therefore, the coordinates here are 200 for x and 0 for y. So these are the coordinates of the turning point, which, as I mentioned just earlier, relate to the h and the k. So in other words, our h must be 200 and our value for k here must be 0. So we can now say that y must equal a brackets x minus 200 squared plus k, which is 0, and so actually y is just a brackets x minus 200 squared. So that gets us so far, but we need to work out what this value for a is. So what we can do is use another point that we know. Well, we know this point here, 0, 75, and we know this point here as well, which is 475. So I would suggest the easiest one to use would be this coordinate here, and the coordinates of this point over here are just 0, 75. So if we substitute this into this equation, we can now work out the value of a. So sub 0 and 75 in. So 75 equals a brackets 0 minus 200 squared. So in other words, 75 equals minus 200 all squared times a. Well, 200 times 200 will have a 4 with 4 zeros after it, like you can see. So that's going to be equal to 40,000 a. So therefore a is going to be 75 divided by this 40,000. So a is going to be 3 over 1,600. So therefore the equation we're after is that y equals a, which is 3 over 1,600, brackets x minus 200 all squared. And so our equation, which we wanted here, we found, which is this equation here. And unfortunately that squared has looked a bit strange, so I'll just put squared in a bit clearer there. Still not perfect, but that is a squared. That's a power 2. So let's move on to part B. For part B, we need to find the height of the cables above the road at a point 100 metres from the centre of the bridge. So what we could do with reminding ourselves over here is the equation we just had from previously. So that's the equation we had from part A. So a point 100 metres from the centre, well, we knew that the centre from part A was at 200. So 100 metres from the centre, we've got two options. We could either go 100 to this side, which should be at 100, or we could go 100 to the other side, which should be at 400. So we've actually got two different options. We can pick whichever one we want to be perfectly honest. So we could either go for this one over here, or we could go for the other one. So if I just put the line in going across, just to illustrate what I'm getting at. So, as I say, two options. You can pick whichever one you wanted, doesn't particularly matter. So I'm going to go for, I think today, I feel like going for 300. So I'm going to go for this point over here. So for part B, we need to work out the height of the cables above the road when x is 300. So we can just take this equation we've worked out from part A and just substitute in x equals 300. So when we do that, we get that y equals 3 over 1,600, brackets 300 minus 200, all squared. So if we just bash this into our calculator, over 1,600, brackets 300 minus 200, close brackets, all squared. We get 75 over 4, which is 18.75 metres. We could round that to three significant figures if we wanted. That would be fine, 18.8. Or because it's a relatively simple decimal, we could leave it as 18.75 for now. So just leave that as 18.75 metres. So we've now polished off question 2. Question 3, we're going to be modelling a shot putter's throw of the shot in a shot put competition. So this shot putter, we're told, releases the shot, which is just the name of this really heavy metallic ball, from a height of 1.68 metres above the ground. The shot reaches its maximum height above the ground of 3.3 metres at a horizontal distance of 9 metres away from the point of release. So we're taking this real-life scenario and applying it to a coordinate grid like this. So we've mapped on the maximum height, 9 metres away horizontally, and a vertical height above ground of 3.3. So what we need to do now for part A is, using these conditions, we need to model the trajectory of the shot as a point particle following a quadratic path. Give the equation in the form y equals a brackets x minus h all squared plus k, where a, h and k are constants. So apologies, I've just noticed here that should say y in front, so y equals. I should say y, but forgive me for that, if you will. So this here is the completed square form of a quadratic, and we need to be comfortable and confident in knowing that this completed square form is useful for the turning points of a quadratic. So h, we need to know, relates to the x-coordinate at the turning point, and we need to know that k relates to the y-coordinate of a turning point. Now luckily the question's told us this. Okay, we've got the maximum point here. Okay, so this here is the maximum point of the trajectory. And if you read the question carefully, we're told that it reaches a maximum height at a horizontal distance of 9 metres away. Okay, so we know that our x-coordinate at the maximum is 9, which it says here, of course, as well. And the y-coordinate at the maximum is 3.3, which it tells us in 2 points in this question. It tells us here maximum height of 3.3 metres, and it's also kindly labelled for us on this coordinate grid. And so we can just say that our h is definitely then 9, our k must be 3.3. So we substitute these in for the conditions. So y equals a brackets x minus 9 squared plus 3.3. So now it's just a case of working out what this a is. What we need to do for that one is to substitute in some other information if we know it, which fortunately we do. We're told the athlete releases this shot from a height 1.68 metres away, sorry, of a height of 1.68 metres above the ground, sorry. That's when x is 0. So he releases it when he's at a horizontal distance of 0 away from himself, obviously really. So we do know this point which we can use. So that's at coordinates 0, 1.68. So we can substitute this into this equation here. So let's substitute 0 and 1.68. So we have 1.68 equals a, x, which is 0, minus 9 all squared plus 3.3. So now we just need to rearrange this. So we could subtract 3.3 from both sides. So 1.68 minus 3.3. Let's just do this. 1.68 minus 3.3. That gives us minus 1.62. So we have minus 1.62. equals a multiplied by 0 minus 9 all squared, or minus 9 multiplied by minus 9, that's going to be 81a. We can then divide by 81 to work out what a is. So a is going to be minus 1.62 divided by 81, which is minus 1 over 50. So if we want to, we can leave it as this fraction, or we can write it as a decimal and say that a is minus 0.02. So in other words, the equation is y equals minus 0.02 x minus 9 squared plus 3.3. So that's our equation for part A. For part B, it says using the model from part A, find the value of x that corresponds to the shot hitting the ground, and hence find the recorded length of the throw. At this point, we need to remind ourselves of what we had from question A. So we had this equation here. Of course, we worked out what A was, so A, of course, was minus 0.02. So we can go one better than this and actually type in what A was. So we worked out, of course, that A was minus 0.02. So we can use this to work out what the recorded length of the throw was. So the length of the throw is going to be recorded when the shot hits the ground. Okay, so we can just substitute in that y equals 0. So shot hits ground when y equals 0. So what we can do here is just take this and either use the quadratic formula or just rearrange this completed square. So first of all, we say that 0 equals minus 0.02 x minus 9 all squared plus 3.3. We can subtract away 3.3 from both sides, and we get that minus 3.3 equals minus 0.02 brackets x minus 9 all squared. We can now divide through by minus 0.02 to just have x minus 9 all squared on its own. So minus 3.3 minus 3.3 divided by minus 0.02, that gives us 165. We can square root both sides now. So x minus 9 equals, remember, plus or minus root 165. Therefore, just add 9 to both sides, so therefore x equals 9 plus or minus root 165. So let's try both options for this. So first of all, we could maybe try that it's 9 minus root 165. That gives us a negative value. This negative value would correspond to being over here. Okay, so that's the second root which we need to just reject because it's negative. So just by the symmetry, that's one root which doesn't apply to this real life context. So we're after only the positive root. So we're after 9 plus the square root of 165. So we can just say goodbye to the negative option and leave it as the positive. So x must be 9 plus root 165. So if we just toggle back, replace with a plus, press equals, and give it to a suitable degree of accuracy. So using our model, which is rather crude, if in doubt, 3 significant figures. That's the golden standard, unless a question tells us otherwise. So to 3 sig figs, that's 21.8 meters. So the recorded length of this throw is 21.8 meters. For part C, we need to provide one valid limitation or criticism of this model. So there's a few we could give. So I'm just going to run through 3 different solutions that you might want to apply. So either one of these is worth 1 mark. As long as your criticism is valid and make common sense, that's absolutely fine. In my head, the most obvious criticism or limitation will be this model assumes no air resistance. Okay, a shot put is fairly large, so although it's very heavy and dense, it will be subject to some air resistance which will alter both the path and the distance it's thrown. Because this model doesn't take into account the air resistance, that means it's going to lose a tiny bit of accuracy. Another criticism would be that this model assumes the ground is perfectly horizontal. So this x-axis here has been modelled as perfectly horizontal, which you'd expect it to be, of course, but in real life, the field, or this shot put arena, wherever it's being thrown, will be going slightly uphill or slightly downhill, even if it's marginal and only a tiny bit. It's virtually impossible to have a perfectly horizontal surface. A third criticism you might want to mention is that the shot is modelled as a point particle. Okay, the shot isn't the size of some grain of rice or a grain of sand. It is actually quite large. It's several inches in diameter. So because it's modelled as a point particle and not as its actual shape, that again will affect the accuracy of this model ever so slightly. The last question I've got for you is question 4, which I've put in red, a challenge question. It's not too much harder, but I've noticed people struggling more with this type of question, so if you do this and manage to get it, then well done you. So the brief of the question is as follows. We're going to model a parabolic arch which has a maximum span of 35 meters across and a maximum height of 8 meters at its centre. For part A, we need to find a quadratic model that links the height of the arch, which is a function of x, h of x, with a horizontal distance from the centre of the arch, x. So give your equation in the form y equals a brackets x minus s brackets x minus t, where a, s and t are constants. Now, a suggestion is to sketch this graph in pencil and then carefully choose where to place the relevant intersections with the axes. A subtle wording of this question actually is a big clue to us. So it says we need a model that links the height of the arch, h, with a horizontal distance from the centre of the arch. So we know when the distance from the centre is 0, in other words, the actual centre of the arch, when x is 0, we're 0 meters away from the centre, in other words, this is the centre. We're told it's got a height of 8 meters at its centre. So we know when x is 0, h of x needs to be 8. Okay, so what we're going to be having here is its highest point is when x is at 0. So a very crude sketch here. I'm going to give you a cheated one in a minute because I'm going to cheat and give just a computer generated model instead because my sketches are pretty awful. So if that's y and that's x, what I'm basically saying here is that y is at a maximum when x is 0. And so for these axes, although this is tempting to draw it like this, what we actually need to do is just to imagine the y-axis is actually in the middle. Okay, so the origin would actually need to be here, and y at the origin, sorry, when x is 0, is 8. And so we can add this to our sketch, which we've got here underneath this writing. So the parabola is going to look something like this. So in a much nicer looking way, we're going to have something like this shape. So like I've said before, this maximum is at 8. As well as this, we're told that the maximum span is 35. So from here to here is 35. So if that's going to be the origin 0, that's going to be 17.5, and that's minus 17.5. So adding it in bit by bit, like I say, the maximum height is 8 when h is 0. Over here we have plus 17.5. Down at this end we have negative 17.5. We've now got all the ingredients to form our equation, which we need to do in this form. Now, you also need to remember this form of the equation is what I like to call the root form. So s and t are the roots. Okay, so this is the root form. So if we're going to graph this arch as such, it's going to have roots at x being minus 17.5 and where x is positive 17.5. And when a quadratic is written in this form, s and t relate to the roots. So in other words, s is minus 17.5 and t is 17.5. S and t in any order are minus 17.5 and positive 17.5. And so this equation, y equals a brackets x minus s brackets x minus t, becomes y equals a brackets x minus 17.5, that's x plus 17.5, and minus t is now minus 17.5. So, just using the fact that we've gone for s being minus 17.5, minus a minus is a plus, and but t is positive 17.5. So that's all well and good, but obviously we need to work out what this a is. To work out what a is, what we need to do is substitute that when x is 0, y is 8. And so we can substitute this point here, and that point here is of course 0, 8. So we can substitute this in now to work out what a is. So sub in for x is 0, where y is 8, and what we then have is y, which is 8, equals a brackets x, which is 0, so 0 plus 17.5 is just 17.5, 0 minus 17.5, which is just minus 17.5. So we need to do 17.5 multiplied by minus 17.5, so we can do this easily enough on our class whizzes. 17.5 times minus 17.5 gives us minus 306.25, and so 8 equals minus 306.25a. So therefore a is going to be 8 divided by this. So 8 divided by that previous answer gives us minus 32 over 1225. So therefore we've got our equation now. So the equation is that y equals minus 32 over 1225 brackets x plus 17.5 close brackets, open brackets, x minus 17.5. So we've sorted out part A. That's our equation for the arch. Let's have a look now at part B. Part B, we're told a wire from which decorative images will hang is to be fixed horizontally, so going across, the inside of this arch, somewhere like this, at a height 5 meters from the ground. Find the minimum length of required wire for this and round the answer to the nearest centimetre. So if it's going to hang going horizontally across at 5 meters high, the wire, which I'm going to draw in blue, is going to be something like this. So 5 meters high going across. So effectively we need to work out the length of this blue line. What we need to do is remind ourselves of the equation from part A, which I've just popped on here. So that will help us massively. So all we need to do here is work out, in fact, there's two options to this which I'll mention. We need to work out this x-coordinate here and this x-coordinate here, and then do one subtract the other to find this distance going across. So that's one method we could use. Another method we could do, because this is a parabola and has inherent symmetry, we could just work out one x-coordinate, which tells us the difference between 0 and this x-coordinate here, and then double it to get the full length going across. If we double it using the symmetry, that tells us the length of the whole wire. So in fact, maybe let's go for that one. So let's just say what we know. So we know that the wire hangs at 5 meters high. So wire is at a height of 5 meters. So this can be substituted in. So let's sub h equals 5 into the equation. So 5 equals minus 32 over 1225 brackets x plus 17.5 x minus 17.5. So let's just rearrange this so that it's an easier thing to process. So we could divide the 5 by this awkward looking fraction. So we just have x plus 17.5, x minus 17.5 on its own. And in fact, this here is just a difference of 2 squares. This thing here I've just underlined is x squared minus 17.5 squared. 17.5 squared is this, minus 306.25. So x squared minus 306.25 equals, we're going to take this 5 and divide it by this fraction, so we're just left with this. And so 5 divided by negative 32 over 1225, that gives us minus 6125 over 32, which is minus 191.40625. At this stage, let's not round. Only round off at the last stage of a calculation, so you don't introduce any rounding error by mistake. So we have minus 191, and the decimal part was 406.25. So if we add 306.25 to both sides, we get that x squared equals this value here plus 306.25, which is 114 point, what was it now? 84375. So therefore x is going to be positive or negative the square root of this number here, 114.84375. So let's work this out. So just square root this number here, so square root that value. we get 10.717, let's say, to 3 decimal places. So minus 10.717, so that's minus 10.717, or positive 10.717. So now we can work out the length of this wire by just doing 10.717 minus itself. In other words, 10.717 multiplied by 2. So if we just double this value here, the length of wire needed, we will have worked out. So the length of wire needed is going to be 10.71, whatever it was, 6 blah blah blah, multiplied by 2. So double this, we get 21.433 and so on. Now how accurate do we need to give our answer? It did say that this is needed to the nearest centimetre, and so we're going to do 21.43. So the length of wire needed would be 21.43 meters. It says round to the nearest centimetre. In fact, it have to be 0.44 to make sure you've got enough wire. But because we're told to round to the nearest centimetre, we must follow these instructions absolutely to the T, and we get 21.43 meters. In other words, 21 meters and 43 centimeters. So that's all the questions I've got for you. I hope you found that useful. So you'll see this time and time again as we go through this Year 12 course, and again, in fact, the Year 13 one as well. So I hope you found those questions okay. If you found them challenging, that's not a bad thing, as long as you struggled through, stuck with them, and got to where you need to be by the end. Thanks for listening, and you'll see me next for the next set of notes, which will be Chapter 3. Thanks again, and I'll see you all soon.